Hey, good evening, everyone. Today we'll start with the remaining parts of 3.10. There's two sections. One's titled differentials. They also put linear approximations, so I'll add that to this. Differentials and linear approximations. All right. And 3.11 is a whole new set of functions called hyperbolic functions. We won't go in deep into 3.11. I don't want you to think that's a section we spend like 2 hours of class on one section, but it is part of the course curriculum. It's one of those sections, the math department always debates whether to keep it in there or not, or remove it, but hyperbolic functions will appear in a differential equations course. They appear from time to time in the Calc 2 and Calc 3 course. So they allot like, just like a half hour for it. They're like, oh, let's just do like a half hour instruction on it. So, although we'll hit a light, you'll get an idea of what they're all about. And then 4.1, I think we can get into maximum today. I'm gonna draw an image. I got most of it drawn here on page 253. This is in 3.10. And when you all see this tangent line at some point x, there's a tangent line at the point x. And I picked another point on the curve, just like they did in this image. And this is figure number 5. But it's the best picture in that whole section. I just picked another point here, just like they did. And we can call this x plus change in x, right? All right. So what's going on here is, from here to here, stop. Can I call that change in x?
Yeah.
That's change in x, right? So, we'll finish the picture together. Like, all right, so from there to there, I can call that distance change in x, true?
Mm-hmm.
Now I'm going to go vertically, from here to here, and that point's on the curve. So can I call that change in y?
Mm-hmm.
Good. Change in y. And if I did compute change in y over change in x, actually, I would get the slope of a secant line right there, right?
Yep.
Yeah, that's change in x and change in y and change in x. Now, we've been talking about derivatives, like dy dx, derivative of y with respect to x. Well, that's a ratio, isn't it?
Mm-hmm.
So I want to show you where is that in this image. First of all, you could say change in x is equal to dx. So both of those would have the same distance. But just like they did in this image, dy would go from here all the way up to there. All right, so I'll just kind of go like this. Look, from here, I'll go all the way out here. From this location to this location, that's dy. And dy dx gives us what? Slope of, yep, slope of the tangent, the curve.
Why dy is going so up?
Because of that ratio, we can think of this as a ratio.
Uh-huh.
Dy over dx would give me the ratio, the slope of this tangent. Does that make sense?
Oh, because
Yeah.
the slope is same. Okay, got
Yep,
it.
that's right.
Okay, got it.
But you all can tell, change in y is not equal to dy, is it?
Yeah.
But they're close to each other in this image, aren't they? So it's just something, if you want to make a note of that, you go, this was dy, change in y only went from here to here. But they're close to each other. They're close to each other in this image here. Dx does equal change in x. So of all the images they put in 3.10, that was my favorite by author James Stewart. Right, I like that one. And I'll leave that up there. But what we're saying is, okay, well, we know this. Everyone agree?
Mm-hmm.
But what if you looked at just dy separately? It's f prime of x,
Times.
put that over here,
Mhm.
yeah. And there's a name for this. So what's that alone? This is called the differential. It actually has a name, so you can call it the differential. dy is the differential. And sometimes you like to see it. That's why I like this image. Can I see it mathematically? Can I just get an image of what you're talking about?
So,
The differential.
so differential is not the same as change in y.
That's right, but how about this? Differential is not the same as change in y. But we can tell they're very close to each other.
Yeah.
If, as long as the change in x is not too far.
Yeah.
You all like that? And feel free to write something about that if you want to just jot that down. I think this image kind of tells a story. As long as change in x, you don't go too far away. If I went way far away, do you agree? I think the dy and the change in y would have dramatically changed in terms of their difference. Do you agree?
Mhm.
But as long as change in x is small, you didn't go too far, you just went, stopped. Then we can tell that change in y and dy will both be close to each other. It's almost like I could say this. Change in y is roughly approximate to this, as long as change in x is what?
Small.
And I can put like very small just to emphasize it. So those would be, very close to each other. So these would be very close to each other. They're true as long as change in x is really tight. Can you see that? So if you shrunk change in x, look at that. What if change in x was like, whoop? Well then, there's change in y and there's dy. And wouldn't they be almost on top of each other? Cool? Is that what
This is kind of like the delta epsilon function.
Exactly right. That's it. So that's my favorite image. So if you hear this word differential, you can almost make an image of it. You go, okay, I got it. Is delta y, is dy equal to change y? Nope, it isn't. It is not. It's called the differential. We know it comes out when we see this representation. We can write it as f prime of x times what? Dx, right? We can write it that way. And that's what you have. Or we're going to use this, everyone, to do what's called a linear approximation. But that's that. I like to show you that. So you get an image of it. dy. You call it a differential.
Now, f of x is the that curve, right? Yeah, sorry.
That's right. That's right. Everyone, let me put that here. This curve was f of x. That curve right there, this curve going like this, was f of x. That was just the tangent line drawn at x. Best picture out of 3.10. Helps us make sense of, oh, differential. What is it? I like this. The author did a little blip on application of physics on page 252. And he wrote this. All right? He goes, add 0. He's talking about physics. So everyone, add 0. That means that x equals 0. And he wrote this. You go, what? He goes, add 0. Sine of x is close to that. And he's talking about a linearization. You might be like, what are you talking about? We'll talk about a linearization here in a second. I'm going to draw a straight line. Linearization is a linear approximation. So another word for linear approximation is a linearization. Well, what's that? It's simply just drawing a tangent line. So linear approximation, linearization. Can you come up with one other term? How about tangent line approximation? Tangent line approximation. All right. Well, what the heck is this about? Well, everyone, to understand this, they should applications of physics. Why is sine of x near x when x is near what? And x is near what value?
0.
0. Because what's the sine curve doing at 0?
0.
It's like this. So let's say, and then its sine curve, doesn't it take off like this?
Uh-huh.
But if you're right near here, and someone's trying to find out like sine of 0.2 or sine of 0.1, notice I'm using x values very close to what?
0.
0. And someone doesn't have a calculator or table of sine ratios or anything like that,
0.
they could use the tangent line here. And you go, what's the tangent line drawn to the sine curve right there? It's the tangent line y equals x.
Yep.
And they could use this to make approximations. This equation right here, y equals x. Again, approximately, what's the sine of 0.1? Sine of 0.01. You go, oh, well then sine of 0.01 could be roughly 0.01.
Mm-hmm.
Cool. But we're going to do this with the square root function. So So don't worry about that, but that was on page 252. So let me erase this. This is what I'm talking about. We'll make sense of this. We're going to do a tangent approximation, or a tangent line approximation, or a linear approximation. Or in other words, we're going to find what's called a linearization. Now here's the problem. We're going to use the square root of x function, okay? Think Sal's going? Take notes from? Oh, thanks. All right, Owen. You and I are going to find the linearization. Okay, I'll put in parentheses, linear approximation. We can call it L of x. We're writing as a function, L of x. Of the function f of x equal to the square root of x. All right, now I gotta pick a point. I gotta pick a point. But I'm not gonna pick 32. I'm not gonna pick 43. I'm gonna think of something that's just a perfect square. What are some perfect squares?
64.
I like 64. What's another one?
81.
81's great. 16. I'm gonna pick one of these. Okay? I'm gonna pick one of these where we got the what? Just some perfect square. 100, 81, 64, 16, 25. I'm gonna do this so we can get an idea of what these linear approximations are all about. So, all right, you know what I'm gonna use? I think I'll use 9. Okay? All right. I don't know why the author likes to use the letter A. But when A is x, if you want to say x equal to 9, go right ahead. I wrote it A equal to 9. Because I noticed the author writes that in the book. I'm going to use A equals 9. It's at the x value 9. So we're going to find a linearization at A equal to 9 or x equal to 9, A being some x value. Okay. And we'll do a part A, part B. Let's make this part A, we'll know part B. We'll use this linearization we find to make an estimate. Cool. All right. Well, what's the linearization? It's going to be a tangent line like that. So when you hear this phrase, you go, what is this again? It's a tangent line. It's going to be a tangent line drawn to that curve at what value? X equal to 9. And you already know how to do that. But that's what we're going to do. We are going to draw a tangent line to the curve y equal to square root of x at x equal to 9. And we'll call it the linearization. Okay? So, let's draw a picture. Let's just get an idea of what this looks like. It's always nice to see this. Doesn't the calculator do this too? Yeah. So if you want to look in your calculator, you can too. Here we go. All right, what's the square root function look like? Oh, good job. He goes, ooh, like that? Yep, you too. Everyone else? You're like, that's good. Just goes like that. Just be shooting off like this. So 1, 2, 3, 4, 5, 6, 7, 8, 9. But how high will get at 9?
3.
So I'll just go like that. Stop! That curve keeps going. Whoop. And that's the point 9 comma.
3.
Oh, let me go to you, Kayla. Look, I'm like, all right, they told me 9, but I'd like to know the y value. So I'm going to take the 9 and substitute it into the original, right? Into the original function. Square root of 9 is a 3. And then you and I are going to find this yellow line. Oh. There it goes. You go, what is that thing? I'll tell you, that's L of x. The tangent line approximation to that curve at the value that we mentioned. We're going to find L of x. All right. How do we do this? I want to start with point slope form. All right, so I'm changing the color. I'm going to show that color. This line is y minus y sub 1 equals m times x minus x sub 1. That's that yellow line. That's the tangent line. Right there. That's the tangent line I'm looking for. I think in my last step, I'll write L of x. Does that sound good, everyone? I'll wait till the end, I'll call it L of x. It's the y, I'm gonna call L of x. That y right there, I'll call L of x. Now I get to put the point in. That's a 3. There's M. That's a 9, so far so good?
Mm-hmm.
Now you all have been great with this, especially from grading the last test. This thing. How do we find it? It's the derivative, right? Everyone agree? It's the derivative. So, that's f prime of x. I know your f prime of x. What's the derivative of that?
1 over, there you go.
Man, some of you just have that thing memorized now. But when we did do power rule, right? If you have to take a second to go, okay, that was x, right, Amber, x to the 1/2. We took the half in front, then we decreased it by what? By 1. Do you want to see that? I'll do it.
Sure.
Just, oh, I sure will. This, it comes up so often, you might even find yourself going, I'm just going to remember that. I'm just going to remember that that's it. But what happens is, we're doing power rule on that thing. You already had x to the 1/2. There's that. You go, what's that prime? You said, well, a half in front, then we decreased it by what?
By 1.
But then, I could
Then you put all-
take that down here. But then, that means I could put a what? Hat on that thing.
Yeah.
But some of you might have been like, I've already seen this 10 times. I may start just memorizing this thing. It's up to you though, Amber. We can always roll through power rule, right? True?
Wait, but it was just M though.
That's right. That's going to be the slope. That will be, the derivative will be that M. But, I'm not going to shove all that there. Because I'm going to evaluate this at what value.
No.
We're going to put a number there. We're going to find the actual slope of that curve, of that tangent. So you're like, okay, here, I'm just going to drop a little line here. At what x value? You have to call it A, all right, at x equal to 9. And what's 1 over
1
2
6.
square root of 9? What do you get?
1 6.
1/6? Okay. So that's 1/6. Get that out of the way. We found it. You're a 6th. You're 1/6. So this is really it. The only thing is, when you talk about it as a linearization, L of x is a linearization, the linear approximation, we solve for y now. So in this case, we will isolate y. So can you help me do that?
Yeah, sure. Y equals
Want to
to,
distribute first or add the 3 first? It's up to you.
Distribute.
Distribute first, okay. I get 1/6 x minus 9/6. Want to reduce 9/6? 3/2.
3 halves.
Y minus 3 equals 1/6 x minus 3/2. There, I like that, looks better. Now how do you get that minus 3 off that side?
multiply by 3.
Add.
Oh, add and multiply.
That's what he meant. That's what he meant, right? And what's negative 1.5 add 3?
3 halves.
Yeah, I think I'll write it as a decimal if you don't mind.
1.5.
Sometimes 3/2 looks weird, students, so I'll write it as a 1.5. Here it is. Y is 1/6 x plus 1.5. The calculator shows this, if you recall, except the calculator might say 1.500000009. Right? Now finally, look what I'm going to do. That's all that. That's my linearization. This is the answer. This is what they're asking for. You got, what do you ask? Find a linearization. Find a linear. That's the linear approximation to that curve at that point. Yeah, you go, tangent line. You know, what's the need for this? I think they really kind of see a need for this with this math problem, and we're going to have to back up like 100 years. Okay, so we back up. That'd be what year? 1915? So back up to 1915. And then when someone said they want you to estimate the square root of 10. Okay? Use this linearization now. They go, hey, do you know what the square root of 10 is? Well, in your head, you know it's just a little higher than what? 3? But I'm telling you, isn't 10 really close to a what? 9. So I want you to look at this image. The square root of 10 would be right on that curve. Does everyone agree? But if we use this linearization, we're going to be a hair above it. We're going to be very close. Do y'all see that? Everyone see that? We'll be really close. So what we'll do is, we're going to use, we'll make this part big. Use your own linearization to estimate the value of the square root of 10. So don't give me the exact answer to square root of 10 on the calculator. We're going to use this linearization. Okay?
But would they have the same value because we took x as 9 over here? Would they
That's
be-
right. This is what's neat. So what we're going to do when we do this, everyone, to answer that question, if we're going to use our linearization, we're talking about, we're using that yellow line here, right?
Uh-huh.
So we're going to use this equation. But go back, it's 19 what?
15.
No, it's 1950. There's no calculator. Like, I don't even have any tables near me. But what we're going to do is you and I can see this image. We know calculus. We know that's the square root of x curve. And we know we've got a straight line here. And we know 10 is very close. So all we're going to do is, we're not going to plug square root of 10 in here. We're just simply going to plug in what number here?
10.
Yeah, so look at this. You and I are just going to plug in the number 10 into our equation. It should give us a number that's very close to what? Whatever the square root of 10 is. Does that make sense?
Mhm.
So when this is asked, use your linearization to estimate square root of 10. We're not throwing square root of 10 in here. We're just throwing in what? The value of 10. Go ahead, Josephine.
Could you do part A, but just do A equals 10 instead of A equals 9?
Nope, wouldn't work. Good question. Because we got to make the tangent. We used the tangent line approximation at a number you and I were familiar with. And I think to really understand the problem, Josephine, back it up 100 years. We didn't know what the square root of 10 was exactly at. You know, no calculator. Hey, what's exactly the square root of 10? 5 decimal places. What is it?
3 point something.
Right? And you don't know it, true? So that's why, I mean, that's really, you go, okay, so when this problem was posed to us, here it is, and it was given to us, they used a number that we knew we could exactly get from our knowledge. But then we'll use it to estimate some kind of goofy number that we wouldn't know. You go, well, I don't see no value to this, because now it's 2015, I can just hit this on a what? The calculator? But I just get a sense of what linearization is all about. If we back it up 100 years, we're like, okay, you know what's going to be neat? Watch how accurate our answer is. We're going to see how accurate. So we're going to plug in what number into this? So look what we're going to write here. You're going to just go L of 10. That's what you're finding. I should put it in yellow. Here. You're going to find not L of square root of 10, but L of
10.
And I hope this image helps you see it. Look, it's like, it's going to be like, yeah, it should be really close to what it approximately is. And then afterwards, we could check how much the error is. Like, we'll see, we'll be accurate, I bet, to at least 1 decimal place. If some of you in your head going, it's probably 3.1, or I don't know, maybe it's 3.2, right? Maybe it's 3.01, we'll see. All right, plug it in there. See, it's year 1915, we don't have a calculator, you and I can do this math. Everyone, what's 10 over 6?
0.167 or something like
Yeah, 1.666, right?
that. Yeah.
1.6 repeating. 1.6, because it's 5/3, everyone, right? We know that. 1.6666. All right, what's a 1.6666666 plus a 1.5?
3.1 something.
Yeah, what would happen to that? Well, think about it. You got 1.666 and then you add a 1.5. 3.1 and then a bunch of what?
3.166.
So I'm going to do this. Put a line over it. Can you write that as a fraction? Of course you can. But to really see the meaning behind this, I want someone now to hit the square root of 10 on the calculator. Let's see how close we are. This is our answer. Here it is. This is the answer.
Yeah, 3.162.
3.162. How many places were we accurate to?
2.
We're accurate to 2 decimal places by this technique. Isn't that cool? But do you all understand? I didn't use number like 13, because if x equal to 13, what would happen between the distance between the curve and the line?
Higher.
Yeah, it would have spread apart and it wouldn't have been as close. Does that make sense? So this is called the linear approximation or linearization. When you're in, who's going to Calc 3 eventually? All right, Calc 3, you get It'll be three-dimensional, and you'll have a surface. So think of like a sphere. And you'll get a tangent plane to the sphere. All right, and then what can you do there? You can find what's called a tangent plane approximation. Cool? And you go, oh my gosh, it's going to be so confusing. No, it's going to look just like this thing. It's going to look just like this right here.
It has to be in slow form.
Oh, slope-intercept form. Yep, that's exactly what it is. Hey, if you notice here, this is just like what? L of x was, what was that number there? F prime of what? That was just f prime of x times the x, wasn't it?
Mm-hmm.
Plus that value there. But isn't that cool? I mean, when you calculate, you do these, it'll be called a tangent plane approximation. But they still call it a linearization. You go, it's a plane, I know. You'll do a tangent plane to a sphere. And is there application of this? I think you could see the meaning more in Calc 3 because you got to think of something multivariable. So when think about like, you know, in like the past couple days, just knowing the temperature, does that really tell you how ridiculously it feels outside? No. What else affects it? You got the temperature and what?
Humidity.
Humidity, and that's multivariable. So you got humidity working, then you got what it really feels like, right? Actual temperature, it says 82 degrees. But the humidity is 80%, so what it feels like 97.
Mm-hmm.
And that's what I mean, you got this multivariable function. You got two things going on, but you can do stuff like this to approximate what the temperature would feel like. Cool? So that's where we're going with that. But any questions on this? Cool. So in the end, not too bad. Isn't it something you go, keep it simple. What do you end up doing when they ask you to do this? You're just making a what? A tangent line. We just put it, like you said, in slope-intercept form. We solve for y. And we can call y L of x. The only thing is when they do this thing, make sure you don't plug square root of 10 there. You're just plugging in the what? The 10. You're just going, oh, what do you use? Yeah. All right. That's it. Ready for hyperbolic? You sure gonna raise? Everyone's super job, but it is interesting. We're in Calc what?
1.
And here's a linearization. And when you, okay, if I use x naught and y naught rather than point x1 and y1.
Mm-hmm.
And then we solve for what letter?
Y.
Y. But you get to Calc 3, you go, oh gosh, that's going to be confusing for us. No, you're going to love it. You just get an extra what?
Z.
Right? And it is. This is what it turns into. This is exactly the formula. Now, I have to put something in front of these. What letter's in front of these?
M.
So when you're in Calc 3, you do what's called partial derivatives. And that's the note that's partial derivative with respect to letter x. And over here, you do the partial derivative with respect to
Letter Y.
But you can tell you like, oh my gosh, it's just an extension of this. And they call that a tangent plane approximation. So you're looking at a tangent plane approximation here. This was a tangent what? Tangent line. Tangent line. I just want to show you that. So you go, oh yeah, Calc 3 is going to be a blast. You'll like it, but you can actually do estimates and approximations. The application of things like that. You can approximate the temperature of how it feels outside. If you got a table values that you can plug in there for like humidity and some temperatures, etc. All right, hyperbolic functions. Here they are. Now I want to tell you what page they're on. I'll put them on the board. They're on page 257. And they're called the hyperbolic functions. Some of these you might make up your own names for. Yeah, I'm serious. Here's one of them. E to the x minus e to the negative x over 2. The other one? E to the x plus e to the negative x over 2. Should I put a y equal to in front of them? Okay. Now, does anyone want to see what these graphs look like? See, these are the hyperbolic functions, right there. But we're going to call them something else because of the behavior. Now, if you want to see their graphs, everyone, they're shown on page 258. This guy kind of went like this. This guy kind of goes like this. One of them's even, one of them's odd, can you tell?
Mm-hmm.
If you know even and odd functions. Even functions symmetrical with respect to the y-axis.
Mm-hmm.
Odd functions are symmetrical with respect to the origin.
Origin, yep.
Which one's the odd function?
Left.
Yeah, you're odd. You're an even function. But mathematicians got an interesting feel for these. There's an application with these, so we'll do an application problem. These types of functions you can see in actual real life, real world problem. But they looked at the derivatives and they noticed things happen. So can we take the derivative of one of these?
Yeah.
I say, and then we're going to call it something else. Sound cool? Sound good? Let's differentiate that one. Let's find the derivative of y with respect to x to this guy.
So low d.
And something funny happens. And we'll do, oh, I heard it. We're going to do what rule?
Low d high minus high.
Will that work, Owen? Quotient rule
No.
for this one? You can if you want. But what's another way you can do it?
Just take the derivative of each one.
All right. Hey, first of all, he says, can I erase that image? I'll put it up here. Like this. I want to get the derivative of this so you can see what mathematicians kind of discovered themselves. Then take the derivative. He said quotient rule. Absolutely, that's a great idea and it can work, right? But I was wondering, is there another way to do the derivative? Because the denominator doesn't have a variable, it just has a what?
Constant, yeah.
So I might look at this problem as just what?
1/2.
Maybe a half in front. But it's up to you. Please know, you could do quotient rule. Right? You could do quotient rule, but can we look at it like that? All right, so let's differentiate this. All right, that's what. All right, now. Y prime. That means constant what? You stay. We don't need a product rule here. Let's start with that guy.
E to the x.
What's your v dx?
E to
Yeah, that agree?
Mm-hmm.
All right, we got a chain rule here. Be careful, because that's not e to the x. That's e to the negative x.
So that's e to the power negative x times minus 1.
Yeah, you're good at these. I saw that grid. Like if it's e to the 2x, the derivative is e to the 2x times a 2, right?
yeah.
Times that chain. Or e to the 3x, e to the 3x times a 3. Well, derivative of this will be e to the negative x times a negative 1. So, all right, e to the negative x times a negative 1. Well, what's a negative times a negative?
Positive.
Positive.
It's something interesting they realized. You go, what is it? Well, they like these functions, these hyperbolic functions, and they use them. But that derivative is actually that one.
Oh, yeah.
They go, oh my gosh. They like both of these functions, right? Already playing around with these functions. You know what's interesting? The derivative of this function is actually what? That one. And it's funny, we won't do it now, but if you differentiate that function, you know what? You would get that one.
Well, yeah.
You might be able to see it. You derivative of that one's gonna be that one. So they're like, this is funny, this is kind of like the trig functions. That's what they realized. Because what's derivative of sine?
Cosine.
Cosine, right? Sine of x, cosine of x. So that's what they did. So they go, hey, you know what we'll do? Let's call this something. We're going to call this You can't call it sine of x, so they'll just put an h right after sin. So everyone, sin, put the letter what? H, and then parentheses x. We're gonna call that, now what do you wanna call it? Does this sound good? Hyperbolic sine? Hyperbolic sine of x, will that work? But you might come up with your own phrases. You know what I mean? When you're reading it to yourself, you might go sine h, or sin, I don't know. You might do it. Now, so guess what they're gonna call this guy?
Cosh.
Quash. We went around the entire math department a year ago. To every colleague, do you call it kosh or kosh? No lie. I got like 15 answers of kosh, and I got 15 answers of kosh. So I don't care what you call that thing.
Kosher.
You know, it's hyperbolic cosine, right? Hyperbolic cosine. Now, this is the funniest thing. Students sometimes, when they're hitting these on their calculators, you can go to your catalog, you'll see these. Do you know where catalog is on your calculator? You want to get it real quick? Hit second zero. Scroll down to either C or S. You'll see a COSH somewhere. You'll see sine H. It's in there. But they're representing what? These two. These are the functions they're talking about. They just named it something else. Isn't that cool?
Oh,
Did you see it in the list?
yeah.
Is cosh in there?
Cosh, -1.
Oh, that would be inverse cosh. That'd be the inverse cosine. Right?
Yeah.
Hey, I'll be honest with you. You might say, hey, we're going to get the inverse cosines in here. No, remember I said the time allotted for this section? They just wanted us to get a what? You know, just a little taste of this stuff, because you will see a couple of these, like maybe in a DE course. But I think we could say this. What's the derivative of hyperbolic sine equal to?
Cosh of x.
Well, here's the way I can write it. Derivative, right? Differentiate with respect to x, you get the cosh, right? Now, don't think this is exactly like trig, because check this out. It's not precisely trig, because the derivative of cosh isn't negative hyperbolic sine, it's just what? It's just hyperbolic sine. Isn't that cool? Isn't that cool? Now there's a bunch of these listed, and if you want to go to page 259, I'm going to put another one down. I want to see if y'all can predict it. What do you think this would be? Now I'm writing something, but I need you to figure out how I came up with this. I haven't drawn that on the board yet. But how do mathematicians refer to this? Isn't that the ratio of what?
Sine over
Oh,
cosine.
you're good. Sine over cosine is tangent of x, right?
Yeah.
And so that's why I remember Josephine were talking the other class a few days ago. It was about the trig identities. And I go, all right, for now, make sure we at least know that one. So this function right here, they're saying take the ratio of those two right there. This divided by that. Which you could do, everyone. You know how to divide fractions, right? Well, guess what that derivative is? Secant squared. And everyone, do they put the 2 after the h? I think they do. Yeah, they like to put that squared like right after there. Like that. I know if you're like, well, for our test, since we hit this section kind of light, you go, which ones would I have to know? It's these two. I bet you have no problem remembering them, huh?
So then secant x will be what? Like secant x, secant x tan x?
Oh my gosh, he just nailed it. He just nailed it. But I noticed something, because I didn't even look at that one. It's actually negative.
Negative.
I know. I won't write them on the board. It's funny, because art is like, how much do they want us to do with this section? They want to make sure the students got a feel for it. Definitely know about these two, but there's more. And he was just asking, is the derivative of hyperbolic secant equal, the derivative of that, is it hyperbolic secant times hyperbolic tangent? It is, but it's negative. Do you see it? You see, he sees it. So it's close though. What they noticed was there's a close relationship starting with these two functions and trigonometry, right? But this is hysterical. When students start doing this, sometimes this will happen to you. You might think you got to be like in radian mode. To do this, you don't have to be in radian mode to hit these on your calculator. Right? Do you see any trig in there? No, they just called them this because of the relationship of how it was. It's almost like identical in terms of derivatives with the trig functions. So you don't have to be in radian mode. Just always remember, what were these functions? There's no trig in there. These are exponentials, right? So don't think, like, you can be in any mode when you do these on your calculator. But you bet, everyone, if you want to find what's going on with that function at x equal to 17, you could hit that on your calculator and put what number right there?
17.
17? I think it's quicker. I think it's easier to type in than this, right? If you gotta find the value of this at x equal to 2, you could just hit cosh of what?
2.
2.
You go to the catalog thing and just.
That's what you do. You just go, it's probably in another menu on your catalog, but you go to the catalog, and you hit that, and then you put what number there?
17.
Yeah, so hey, I'm curious, what's cosh of 17?
3.524.
Is that what it is? Check it out, Kayla, 3.5 what?
3.52549.348.
Yeah?
Why did I get that one?
Oh, what'd you get?
Just really.
Oh, wait.
That's not it, Amber?
I don't think so. I
It's
did
a
the
very big
negative
number.
one.
Did you hit coast by accident?
I think, no, I did,
I apologize.
I did a negative one.
Alright, we'll edit that out.
Like 12 million. Yeah, it's 12 million.
12 million?
Yes.
Yeah.
Give me all the numbers.
12 million? Or?
120774776.
120774. And remember the graph was doing what? It was like this, so when we got only out to 17, this sucker was what? It was high, huh? It was high.
Cool.
Hey, these types of functions, have you ever modeled anything that you're aware of? Go to page, if you got your book, go to page 259, and you're all gonna recognize and structure, and then we're gonna find out if anybody in this class has been up in it.
You can go up?
Who's been in the Gateway Arc in St. Louis? I'm curious. The actual equation that represents that what? Which one of these two does it behave like? It's like the cosh. And
Oh,
there's an
shit.
equation for it. You can look it up on the internet if you want.
But inverse, right? So there should be
No, I
negative.
think the author wrote it. So when you look on page 259, no one in here's been there? Usually I get like one student who's been there. You're like me, you stay in Maryland. This morning in stats, we did Old Faithful, you know, at Yellowstone Park.
Uh-huh.
Who's been to Yellowstone Park? No one's been there either. Well, these places are far away from here. Usually I get like one student who traveled with their parents and been there. But hey, everyone, if you wanted to see the equation for the Gateway Arch, would you go to page 263 and look at that equation? Does anybody want me to write it on the board? Everyone? You want to know it's designed? You want to see the equation?
Number
All right,
48.
there it is. You could have saw this on Wikipedia. So it didn't use this equation, but it has one of these guys, and here it is. Gateway Arch. And this is in St. Louis. But the elevator just kind of goes up like this as it goes around. So you get a nice view of everywhere. But it's probably like, you know, trying to get in the monument. Sometimes the monument's not open, is it? Sometimes they have to do what? Yeah, they got to do a little maintenance and stuff like that. Remember that earthquake a
Mhm.
few years ago? That did some damage to the monument. Do you know that?
But that's in DC, right?
Yeah. And that was the earthquake
It was like,
that was in Virginia,
Uh-huh.
damaged that monument.
In centralized
Isn't that
Missouri?
amazing? Yeah.
Wow.
And you got to ask Professor Major about that.
Oh.
Would you email her tonight?
I had lost it. I
If
don't
you
know.
don't remember, all right.
Yeah.
PG Mazer at AACC. Just say I mentioned that because she was the one who informed me. She went down. She goes, do you know? She went down there. She goes, yeah, I think that somehow got damaged. Like it just, I don't know, damaged, but it shifted. Like somehow the whole monument and everything shifted a little bit. All right, here we go. Y equal 211.49 minus 20.96. Boy, they're never neat numbers, are they? Gosh. So tell me this then. 0.03291765x. Okay, 0.03291765 times all that. Right? That's what they're saying, right? But how does it look? It's got a what? It's like that. But you saw the cosine graph, right? Didn't it go like this? Well, what's in front of that?
Negative.
So that's cool. Now, we're gonna do our own application problem. So I'm gonna do,
So do they use this kind of cost function to make bridges and all?
to make what?
Bridges and all this kind of stuff?
They do.
They do.
And bridges, another place, is power lines.
Gotcha.
I want to know catenary. It's just, you ever see the power lines, how they hang?
Uh-huh.
Here's the pole, here's the pole. It's not tight, is it? It's what?
It's like kind of.
Yep. It's like right outside my house. We're just gonna let all the birds hang out on the thing. And the thing just sits right there. Yeah. I'll tell you though, a month ago, man, there's a bird. If I walked outside, the thing would attack me. I mean, it must have built a nest right near my door. But that's what we do. He'd sit up on the power line. I'd come out and go crazy, and I'd go to the mailbox, and he'd just come diving down at me. What did I do? What am I doing? He must have built like right near the house or something. He's upset I had my light on at night, degree math test or something. Turn out the light. I'm trying to sleep in the trees. I don't know. All right, so we're gonna do. This is number 51. It's on page 263. Cool. And I'm thinking for this one. And what I'm gonna change a little bit. Does that sound good?
Okay.
Put like. Because I know I put that as one of our practice problems for you to work. Alright. Here comes the power line. Y equals, they got 20, I'll use 25. 25 cosh x over 25 minus 15. All right. Now, let's only consider this on the interval from -7 to 7. Now, anybody got a calculator handy? Would you help? You're gonna have to play with your window. I want you to go from -7 to 7 and graph that. Now, it should look like a power line. And when it should do what? Slightly go like that. It won't be straight. It won't be straight, but you should see a little.
So put that 25.
But for your window, you're gonna have to look from -7 to 7. If you wanna mess with it.
Yeah, so the line.
Everyone, let me make a note. X and Y are measured in meters. Now I'm curious, how high did this thing get? Someone's gonna have to tell me the y-intercept. How do you find the y-intercept?
X equals to 0.
So what's 25 times cosh of 0 minus 15? You can do it on a blank screen. You got it, Jess. Now what's 25 times cosh of 0 minus 15? And remember, Kaylee, you can just hit it on that catalog button, right?
Yeah.
If you want to type it in. What's 25 times cosh of 0 divided 25 minus 15? How high did this curve get up to? Is it 10? So there's the y-intercept. But what did this curve do? Everybody see the graph? Amber, did you get the graph going?
No,
Want me to help you type it in?
yeah.
We'll go hit that cosh off the catalog.
I think your Y's bigger too.
Yeah, I did -7.
Oh, good call. So you did 25, now we'll get what? Catalog. You want to jump to the C's real quick? See how I got there real quick? Isn't that cool? I didn't like scrolling the whole time. Where's cosh? There it is. All right, 25 cosh. X divided by 25. Common question I get from my online students. Where's the cosh on the calculator? You know, where are the hyperbolic trig functions? Or the hyperbolic functions? Then we hit graph. You know, we can't see it. So any suggestions on our window?
I did 20, the Y
What'd you do for, what was your low?
I just kept it at 10.
Hey, that's cool. We can make the y min like 0.
Yeah.
Y max, how high'd you go?
20.
20. Let's see how low.
Actually, you can do it in 15 too.
I like it. Oh, there it goes. If you didn't want to go so high, we could have gone to what? We made our y min 0. If anybody wanted to make the y min 0, your y min was fine though. And she did y max 20, that's fine. We could have done what? Just as long as you get over 10, maybe 15 or something. Will that work? Oh, there it goes. Like a power line, right? So what they're going on with this problem, they said, here's the function, but it's tied between two poles at these locations. So there's a pole right here. All right, and these are poles right out of the ground. So there's the poles, this is a pole, this is a pole. But this represents the what? This represents the catenary. They call this a catenary. There's a catenary. Cool. Now here comes the question. Everyone, could you find the slope of the curve when it meets the right pole? You find the slope of the curve. That means slope of the tangent line drawn through the curve. When it meets which pole?
Right pole.
Yep, when it meets the right pole. I like this. And if we're only get like, if we're only allotted a little time out of the course syllabus in terms of the outline time frame, they just spend like a half hour in a section. Okay, we'll hit hyperbolic sine, we'll hit hyperbolic cosine, we'll know about their derivatives, and we'll do an application problem. Okay? It's kind of fun. So we're gonna find the slope of the curve when it meets the, I'll just put it, find the slope of the curve when it meets the right pole. All right. How do we find slope of tangent lines in calculus?
Take the derivative of the original function.
So we're saying, everyone, to answer this question, we're going to take the derivative of this function,
Mm-hmm.
and then we're going to substitute what value?
7.
So,
7 agree? That's what we're going to do. Good problem solvers. I like it. Take the derivative of this, plug in what?
So it'll be negative.
7.
So it'll be 20, no.
Be careful though, we're going to have to do show what rule.
Chain.
All right, first of all, what is, before I start, what's the derivative? Because you have to know this, like even on your test. What's the derivative of cosh? Right?
Sine.
Is it negative hyperbolic sine or is it positive?
Positive.
Negative.
Be careful, it's positive. I know. Don't think trig. I know it behaves like trig, but the cool thing about hyperbolic sine and hyperbolic cosine, right? Each one has the other derivative, but there's no negatives. So real quick, derivative of this is just what?
Sine.
Yep. And what's the derivative of sine x?
Cosine.
Cosh x, right? If you get tired of saying, don't you? You'll get tired of going
Yeah.
hyperbolic sine, hyperbolic cosine. So you call it cosh, but I don't know what you want to call that one. I've asked colleagues, and they go, I just say hyperbolic sine, because it's hard to say sine,
or sin hx.
sine hx, right? True. Hey, if you did an SCS on this thing, what would it look like? There would be no what here?
Or
No
positive.
negatives.
No negatives. So when you're in differential equations, maybe a semester or two from now, and you have to take the antiderivative of one of these, it's just going to be that, right? You just go that way. Does that make sense? All right. So we're going to do derivative. Now what's the derivative of the constant?
0.
All right, so that's 0, and don't put that minus 15 in there. Here we go. We're going to get y prime, and then we're going to substitute what number?
7.
7. All right, here we go. What's y prime of x? We get,
Hyperbolic sine.
all right, 25, constant stays in front. Hyperbolic sine. Amber, no negative, right?
Yeah,
No negative. X over what? 25? Maybe another way I'll write this because it helps you see it. Isn't that just 1/25 of an x? Maybe I'll write it that way. Because I have to do chain rule right now. Right? 25 sine, there's my g. And what do I always multiply with chain rule? G prime, right? And if that's g, what's g prime? Here comes the chain rule, right? Chain rule, there's my g. What's g prime? What's the derivative of all x right there?
X.
1/25. Right, everyone? Here comes g prime right away. multiply to all this, 1 over 25. You see that? Are you okay with that, Amber?
Wait, what did you do?
All right,
Oh,
fine.
you just got rid of the, X.
Because this, isn't this like my G?
Yeah.
So hey, when you were doing this like on a test, you do all that, like sine of 2x, you go, oh, the derivative. Cosine 2x times 2. And that's that chain rule. The G prime was the derivative of that 2x. Same thing here. We know that right there, but we have to apply chain rule here. And you're like, okay, I'm gonna apply this. And a lot of you put this where? Up here?
Yeah.
I think it's a good idea. Well, let's move that there.
Which is just 1.
She goes, you're just gonna get 1. So here, I'll drop this down. Remember, that was good. She goes, hey, everyone, this 25 and that 1 over 25 are just gonna what? So I'll write it again, and then we're just gonna substitute what into our calculator. Alright. Now I'm gonna write it back like this, because it looks easier to type it on the calculator. Alright, that's it. So I gotta plug in what number?
7.
So what's the slope of the tangent line? Hey, Josephine, real quick, before I answer your question, why do a lot of online students leave an answer like that? You go, why not? Because they don't know where that is on the what?
Calculator.
Calculator. We'll hit it. We'll get the number. We'll get the decimal reading. Go ahead, Josephine.
Get the 7, because I don't have a problem.
Oh, that was the question posed. It was just asked. That was the question asked. Right?
That's all you do.
They put the 7s, the 2 poles, and the question was, find the slope of the tangent line at 7. I know. Or actually, you know what they said? Look at this. They said when it meets the right pole, Josephine, put this down. But they did mention there were 2 poles located at these locations.
Oh, okay,
They even drew an image. Josephine, they drew a picture to help you see there's a pole right there. And there was a 7. Oh yeah! It's all, I like to go to catalog. I'm sure there's other menus you can find this stuff. But you forget the menu. We always know catalog. So I'm just gonna go, ready? I won't even graph it. We'll just do the value now. See catalog, second 0, second 0. Starts at A. We wanna get down to what, S? I could scroll forever. Take for all. Let's just hit the S. Where is it? Right there? Now I'm at S. Hey, does anybody know how to quickly get to S in catalog? She goes, click on S. Sarah, thank you. She goes, after you hit catalog, find the S on the front screen, and you'll get the S's quickly. That's not it? There it is. Now what do we gotta put in there? 7 over what? Do you have to be in radian mode?
No.
No! People think you don't have to be in radian mode. Alright, what is it? Tell me the answer.
0.28.
And when y'all getting about 0.28?
Yes.
That's it? That's the slope. That'd be the slope right here. That'd be slope of that curve. That's important. I don't hang power lines or anything like that, right? Or telephone lines. A lot of times they got them under the ground now, right? But that slope is actually important to the person what? Designing. They may want, they have a specific slope in mind that they want. This is about 0.28. What was that, the 85?
Is there no units?
Point.
Cool. 284. Awesome, thank you.
Is it in meters?
Oh,
Yep.
yeah.
Meters.
That's right. That's exactly it. Everyone, great job. Are you ready for 4.1? I know, they didn't want to spend too much time in that section.
Don't we still have to find the angle?
Good question. You can if you want. On a test, I don't ask you for that. Right? But you could find the what? Yeah, now if you said, how would I do that? You could build a little triangle here. And you could think, all right, if I went 1 in this direction, and you have this, you could do like a trig ratio there, couldn't you? Do you see that?
Yeah.
You'd be like, oh, okay, the slope of this tangent line, rise over 1, and if you're curious how to get the angle, I'm just going to draw a tangent line like that, and on purpose, I'm just going to make this a 1. If you wanted to find the angle, wouldn't the rise be the 0.285?
Mm-hmm.
Because the slope of tangent line, rise over run of that line right there. And then to get this angle, you can do a inverse tangent.
Oh, okay, good.
You can inverse tan that ratio there and you can get the angle. But Ben, I don't do it. If anybody's curious, I don't. But I want to make sure you knew how to do it. You go, I can inverse tan that thing and I can get the actual angle right there of what's going on there. Because sometimes they use that too. They want to know the angle that it's coming at. Cool. right. Hyperbolic functions, gosh, and sine h. So yeah, this is what's gonna happen. It's gonna be a year from now. And you give me like a differential equations course, and all of a sudden you're gonna have to find the derivative of this guy. And someone probably next to you in your class is gonna go, what the heck is that? And that calc teacher probably skipped over the section. You know, they probably hit a snow day and they just looked at something to what? Remove, and like, I'm not doing the hyperbolic functions. But you'll know that derivative is just what?
Cosh.
Cosh, right? And what's the derivative of cosh?
Sine.
Yep, sine hx or hyperbolic sine.
Now, did they derive this from the exponential functions? That's how they did derive it?
I know.
That's how they did it?
Yeah.
Oh, okay.
But you say, isn't that cool when we did, we did the derivative of that, we're like, we came right to the other one.
Hmm.
But that's how they did the same thing when they were looking at it, and they're like, all right, let's just, since they behave like the derivatives behave like the trig functions, we'll just call them hyperbolic sine and hyperbolic cosine.
Hmm.
But you don't have to be in radio mode, right? Cool. All right, everyone, 4.1. What's in this section? Max and mins.
Is it like the relative max, relative min, and like the?
Amber's already ahead of us, Ellen. She knows all about this. That's good. How do you know this stuff?
I think it was.
Is this a minus b over 2a?
I love it.
I forgot what max it was.
Pretty good, Amber. What are we doing now? We're going to see the applications. This will probably go from section 4.1 to 4.3, but you know, you might have graphs like this, right? But right here, something interesting is going on with the slope of this curve here. Let's call it up. What's the slope right there?
0.
So we're like, oh, okay, f prime equals 0. And we can call this a max.
Uh-huh.
But who knows? This graph might have gotten even higher. I'll just do that. So it's not the absolute max. What could we call it?
Relative.
Relative max. So we can call that a relative maximum. Relative to this area, relative to this vicinity. They also call it a local max. So local maximum, what can we call that point?
Local mean.
A local min or a relative min. What can I call that?
Local max.
Local max. Here, let me make that smooth, sorry. And then it just took off. I hope I kept it as a function. I hope I kept left and right there. There we go. Local min, local max. What's the slopes at all those points?
0.
Slope of tangent line of curve, 0. So, when it comes to finding max and mins, we know what to do now. Get the derivative and set it equal to what number?
0.
0. Cool. And I'll get you a sheet that kind of summarizes all this stuff. We'll get into it, you know, in a second. But very good with that. Are some functions having absolute maxes and absolute mins?
Yeah.
The word absolute means the absolute, right?
Absolute value?
I don't think this one did, if I went like that, true? But who's got some examples of a graph that had an absolute max or min?
X squared.
I love it. And he just came up with a simple example. This graph has an absolute what? Right there, what's going on?
That's
Oh, it's not only a local min, that's the absolute what?
Absolute.
Min.
Absolute min. So some do have absolute mins. What else?
X.
I like this, Ellen. That's a great example. Did you hear
What's
this?
the difference between a local min and a relative max or min?
They're
They're the
same thing.
same thing. Remember that? I mean, you can write that down. Local min, relative min, they mean the same thing.
What
So
about,
vice versa, local, relative, and then sometimes they
And then
switch
there's
between them.
Yeah, and then with the relative min, there's like an absolute rate. Yeah.
Well, now the word absolute,
It's like the
that's
highest-
totally different, you know?
There's like the
You're saying a
highest-
relative could be absolute, yeah, but
But absolute.
here's
one
an
is-
example. It's the absolute lowest point, right?
Yeah.
There you go. So that's an absolute min. He said, could I call it a relative min? Well, sure, I mean, relative to that, but it is the absolute min.
Because the lowest point.
There you go. Jess, I heard you. Something about this guy. Now this is interesting, everyone, because that is the absolute min right there. Do you agree?
mm-hmm.
But the slope of the tangent line drawn to this curve here is not 0. Do you all agree the slope of a tangent line to this curve would be undefined?
Yep.
So we're going to have to put a side note I'll get a sheet to you, but we'll go, all right, if I gotta find max and mins, it's where the derivative, I set it equal to what? 0, and then we'll put a little hush in the parentheses and go, or where it does not exist. Because there will be some what? There won't be many, but there'll be just some rare cases where you could have a function and what? The
Doesn't-
derivative does not exist here. Remember this, everyone? No JVCs?
Mhm.
So let me just go through that again. If when it comes to finding these max and mins, we're like, this is what we'll do. We'll get the first derivative of that function. We'll set it equal to what? 0, and we'll figure out where it equals 0, and we'll say, oh, where it does not exist. Just in case we get something like what? This. And you go, well, what are some examples? And when in mathematics, maybe we got a function that has a what? A fraction, and what makes these fractions undefined? When the denominator is what?
0.
0. So we'll consider that as well. Not only will we find out where the first derivative equals 0, we'll say, figure out when that denominator, just check it out. You never know. It might be an asymptote there, right? Might be an asymptote, not have anything there, but we'll just keep that in mind because, Jessica, you just came up with a great example to say, hey, be careful. Sometimes max and mins can occur where the derivative is non-existent. It's a corner. It's a corner, so we'll look at that as well. Cool. Man, you all are great. Some have some. Anybody have any other functions with like an absolute max or min?
Should sign or
Okay, what?
That was good. Did you hear this? How about the sine curve? We have to go plural though. Why? We're actually saying plural absolute maxes and mins. They're all the same. What's it doing? How high does it get every time?
-1 plus
Oh my
1.
gosh. There's a bunch of that. It's like a tie, huh? The absolute max is what number? 1. So that's how we talk too. You put the answer as the y value. What's the absolute maximum of y equal to sine of x? 1. What's the absolute minimum?
-1.
Negative 1, right? Where does it occur? And you go, a lot of places. Do you agree? At what x value does it occur? A lot of places. You can put that +2 in pi if you want to.
Mhm.
But we'll just say a lot of places. So that was a good one. That one has absolute maxes and mins, right? Now,
What about the one?
can they ask the question, this is what we're going to do in 4.1. Can they ask a question about absolutes if the graph doesn't have absolutes? They can, but when they do this, be aware of something. They're going to cut it off in a certain domain. Okay? So we're going to do one like that. All right? I'm going to give you a function where, Josephine, you know it just goes off forever, like this way or that way, like an x cubed. But it's going to say, find the absolute maximum and the absolute minimum points on the interval from -2 to 4. Okay? So if you wanted to even check this stuff on your calculator for checking purposes, take your window and set the x min and x max from what? -2 to 4. Does that make sense?
So like a piecewise function?
Exactly. But even probably easier art. So if we had a graph, and let's say the graph went like what? Like this, right?
Mm-hmm.
And they go, everyone find the absolute max and min, but they said only on the interval from 1 to 4. You might find yourself cutting off what? You might go left with something like that. Right? Does this make sense? You'll cut off the entire graph if they said only from 1 to 4, and you're only looking from here to here. Now a lot of you are laughing and go, well, this is going to be easy if I look at my calculator, because where's the absolute max occurring? Right there. Do you all agree? Where's the absolute min?
No.
Right over here.
Right here, yeah.
So,
Wait, so does that work for graphs that go just like apart, just like a linear graph?
yeah.
And there's like a relative or absolute max and like a absolute min.
Mhm.
Okay.
So, and what we'll do is we'll just cut it off from some region. But they'll state where to cut it off from. They'll say on this interval. Does that make sense? So, there must be something else to this technique. So, let's talk about this. We're trying to find these, what do we call them? Absolute maxes and what? Mins?
Mm-hmm.
But they're going to cut it off on some certain domain. Okay. Is there another word for absolute maxes and min? Yeah, we can say extrema, if you like that word. If you've heard this before, extrema. It's just a word to mean what? Maxes and your what? Mins, if you like to put it in your notes. So we're going to find absolute extrema. I could have said relative extrema, but 4.1, we're going to start with absolute, right? If you're curious if there's only one absolute max, you can make that singular. If you want to know how that word is spelled as singular, it's this. That's the singular form of that word. Extrema. But plural, it's what?
Extrema.
Extrema. So hey, find the absolute extrema for this function on the interval from -2 to 3. So, can we talk about what we're gonna do? We're gonna find what derivative? First derivative. What are we gonna set the function, set it equal to the first derivative?
0.
0. Why? Because what happens here? Slope is 0. But look at the image I just did. What was here before? It was a graph that went like this, went like this, and then went like this, went like this, like this. But we cut it off on a certain interval. He said only go from like here to here. So for our, directions, our step-by-step process, we're like, okay, we're gonna get the first derivative. We'll set it equal to 0. We'll solve for x. But there's something else we're gonna check. What can we call these points? The end what?
Endpoint.
Endpoints. We're also gonna check the endpoints. Because one of those might be the what? The absolute maximum. Someone got that?
Mm-hmm.
So this is, we only do that if they cut it off on a certain domain. Someone got that? All right, let's do one. So I'm going to page, 281. Everyone, can we do number 49? I was looking for a fun one. What's the page again?
289.
281, I think.
281, yes.
Here it is. Find the absolute. Okay. Maximum. As I'm writing this, isn't this something you could check with your calculators? Yeah, all right, good. Minimum. Values of f here's the function, everyone. 2x cubed minus 3x squared minus 12x plus 1. Now, and if I just stopped right there, you'd be laughing at my question. You'd be like, there's no answer to this, I'm sorry. Because we know about x cubed graphs, don't we?
Mm-hmm.
Don't they just, right? I mean, you can't do this. So right after this, guess what they do? They give you some interval. So they go on this interval. On the interval, 0 to negative 2 to 3. Interval negative 2, comma 3. Now these are x values. So we're going from what? Negative 2 to 3. But I know you might be like, let me go look at the graph. I'm going to go blind on this. I'm going to do this because I can't even see the graph because I don't need it. Because I know the process. I'm going to check the endpoints. What are the two endpoints? And I'll check those. You go, what do you mean I'll check them? I will take those numbers and I will plug them into this equation and see what I get. And I'll record them and I'll write them off to the side. And then I'm going to compare them to something else. What am I going to compare them to? I'm going to get the first derivative. And what am I going to set it equal to?
0.
0. I'm going to solve for x. Right?
If it's the same.
Yeah. Is there a name for that, everyone? When you take the first derivative and you set it equal to 0, or where it does not exist, all right? And you solve for x, is there a name for that point? Yes. In calculus, we call them critical points. So if you want to put that down. Thankfully, they put a name to that. So you don't have to go, the points where you set the first derivative equal to 0 and you solve for x, or where it does not exist, all right? Now, did you want me to write that down on the board? What definition of a critical point?
Yeah, please.
Yeah, okay. By the way, I'm going to give you a sheet to everyone that what? Has all this stuff on there. I had to handwrite it because it was hard to type, so I handwritten, I put it all on one sheet where I did everything from like 4.1 to 4.3, a big summary. But on there you'll see this definition. What's the definition of a critical point? A critical point is a point such that f prime of x is equal to what number?
0.
And then I'm going to put in parentheses, or what? Yeah, just put a D in it for cases like yours, Jess. It is a value that doesn't exist. Do you want another example of a critical point? This is not the square root of x, this is called the cube root of x. I'm just going to draw this graph. You would find a critical point right here. Right there. And you go, oh, that's not even a max or min. True. So now we're determined, we've realized something, everyone. Not every critical point has to be a max or min. Alright? Because at this point, right here, the slope is not 0, but the slope what? Does not exist. Does that make sense?
Mm-hmm.
So you might have, there might be some cases of critical points where you go, oh, that's not a max or a min. It's just a place where the,
Tangent.
yeah, vertical tangent. Slope does not exist there. But we can still call this graph has a critical point at x equals 0. There's not many of these. That's why we just lightly put it in the parentheses, right? See, this is a smooth polynomial. We don't have to worry about this part, right? But this is what we're doing for this problem. We're going to check our critical points versus our what? Endpoints. Does that sound good? And when we're going to find our critical points and our endpoints, and we're going to take each one of these x values and we're going to plug it into what? That. And who's going to win the game? The absolute max is going to be the absolute highest y value. The absolute min is going to be the absolute what? Lowest. And then we're all done. I say we check it on the calculator, right? Although I know some people, Claire, they look at the calculator first, which is fine. I know. It's up to you. I would definitely check this during an exam if you can get the graph going, right? It's going to show you the image. Is there a max and min button? Yeah, but let's treat this as, you and I, we're going blind here. All right, first of all, what's my endpoints?
2 and 3.
Negative 2 and a what?
3.
All right, let's just get a little table ready. We don't have to do it right now, but I don't want to forget about this. Trust me, it happens. In a testing situation, people will forget to check the what? The endpoint. So let's just get it up there, we'll be prepared. All right, let's go over here. These are the endpoints, right, everyone? Here's our critical points. What are our points? Critical points are points such that what? They're x values. So Kelly, they are x values, but what's going on? The
If-
slope of x will be 0, right?
0,
Slope
it
of
doesn't
10.
mean-
So everyone, can you help me take that derivative?
Yep.
All right, here we go.
6x squared minus
6x squared, keep going, Art.
minus 6x
Minus 6x.
minus 12.
And what's the derivative of this plus 1?
0.
0. Don't you love ones like this? We don't need chain rule. We don't need quotient. Don't you love these? Give us more of those. I know. That was nice. All right, so we get all this. But I said all this equal to what? So here come your algebra skills, and I heard Kelly already. Everyone, you crank into this algebra mode, and I love it. She was all ready to do it. You looked at this and you go, all right, I gotta solve that. And I don't feel like doing quadratic formula. Kayla, I remember you and I were doing that quadratic formula the other day. I was like, can we avoid it? Let's factor. You said, what would you divide on both sides? So when I'm gonna do that, I set the first derivative equal to 0, and we're just trying to find x. I can see there's gonna be 2 of them. So she divides a 6 on both sides. So you divide a 6, you divide a 6. What's 12 divided 6? And then look, I divided it on both sides. Well, this is the good news. What happens when you divide a 6 from a 0? Yeah, so that's just 0. Did anyone see that? You go, wait, don't I have to factor it out and leave it there? We're solving this equation. Divide a 6 on both sides. And now we all know how to factor this. Two numbers, multiply to negative 2,
X plus 1.
and add up to negative 1. What are they?
X minus 1 and 2.
X plus 1.
Whoops.
X equals to number minus 1 and 2.
Rock and roll, everyone. So here they are. X equal to 2, critical point. That's a critical point. There's another critical point where? Cool, Josephine.
Did you use the intercept on the calculator to find out the correct answer, or do you have to do it that way?
To find the intercept. I'm with you. Oh, hold up. That's not a bad idea. Josephine, are you saying, let me know, you could go to the y equal button, and not type this in, but type this in. I wonder if you follow her. She's taking out her calculator. She's going to y equals. She's typing this equation in. And then she's looking at the what? The x-intercepts. You would find these.
Or,
That's good thinking.
or you type that in and then.
I don't ever want to say that's not the way to go around it. That's actually good thinking. I love how you think like that.
And you put the other y equals.
Because what you're doing is
We did a
you're
problem
graphing a derivative.
before.
And I like that, Josephine. But you could do that. You would find these values that way. Right? And you just go to 0, right? Or intercept. If you do intercept, make sure you make another equation equal to 0. Okay? What she's using, everyone, you might go, well, why didn't she just factor? Maybe, and I'm not putting Josephine on the spot, but maybe a student's like, no, I'm not big on factoring. You know, I've never had factoring down, but I have other skills. I got another skill set. I have another place set where I can take this tool. I know other ways to what? Find these values. Okay? So Josephine, that's absolutely fine. Cool? Absolutely fine. She goes, I'll just grab that thing. All right, cool. Now, everyone, I made this little table. Let's make a little table for this. What do we got here? X and Y, and what were the two X values?
2.
2 and -1.
All right. Now, be prepared. Sometimes this has happened when you practice some of the textbook problems, everyone. This is going to happen. You're going to get one of these numbers that's a critical point that isn't in this what? Domain? So what should you do with that? Who can answer that? It's going to happen. There'll be at least one. I remember I signed at least one problem. I want to make sure so students can know what to do with it. What if you get a value that's, you get a critical point over here, but it's not in here? You got to toss it. Why? Because the question's only asking what? Only on that what? Interval. Does that make sense? So keep your eyes out for that, Claire. If you get if you got a number over here was like -8, you go, I can't use it because it's got to be between -2 and 3. So we're checking these, that number, that number, that number, that number. Whoever's the highest wins as the max, and whoever's the lowest is the what? The min. If there's a tie, we say there's 2 maxes. If there's a tie between the min, there's 2 mins, right? Sound good? Sometimes there's ties. We know that. You get even functions. True? But where am I plugging these? Don't say the derivative.
No, f of x.
I know what I would get if I plugged these in a derivative. I would get what number? And I get that on tests. Students go, well, at this value it's 0. I'm like, the derivative's 0, but we're looking for the absolute max and min of the function. So put them in here, right here. Get them in. Get them in. Now, I want to tell you what I did. Who likes to do tedious things in math? I know. This is what that tool is for. This tool is now going to become just supportive. Of course, we all know how to plug numbers in equations, right? We've been doing it our whole life. But has anybody ever used value? Let's go here now. I want you to go to y equals. Josephine, try this. Go to y equals. And if you had that derivative in there, I want you to wipe it out. I want you to put this guy in. So now I want everyone to go to their calculator and y equals, put this in there. You might find this easy. It just saves a little time. We all know how to plug numbers in. Of course we do. But this is a nice other feature of the TIs. 83 and 84. I put it in here. If your windows out of whack, just hit zoom 6. If your window's out of whack, just hit zoom 6. Now when I want to get these values. Did everyone get in y equals? Did you hit zoom 6 to get like a -10 to 10 window? Alright. Go and you get a picture of the graph?
Yeah.
Josephine, you got a picture of the graph going? Alright. Go to second trace, which is the calc menu. What's the first thing on this list? By the way, there's a reason it's the first thing on the list. It's very popular. What's the first thing on the calculus? Value. And what I want you to do, hit value, and right away, let's just start typing these numbers. What's the first number?
2.
Hit 2 and hit enter. What do you get?
Negative.
Don't go off the screen. What's this next number?
-1.
Hit -1 everyone and hit enter. What do you get? 8. Keep going. What's the next number?
Negative.
Hit -2. Hit enter. What do you get?
-3.
One more time. What's the next number? 3. Hit 3 and hit what?
-44. Oh, C. Sorry.
What do you get for this one?
8.
Everyone say that? It's just a time what? Time saver. Do you follow me? I know you know how to plug numbers in. But when it comes to, you could save sometimes 10 minutes where you'd be sitting on the front screen going, you know what I mean? The value button. It's very helpful in this scenario when you got to do this comparison. Everyone think about, what if I got 6 critical points? I'm like, oh gosh, I can compare all these. Does that make sense? Now, who won this game? Who's the absolute max? Is there a tie?
-1 and 3.
Yep. Now, how's the language? This is how we say it. All right? It's like, how do we fill this stuff in for these problems?
It's -8 for 3.
Yeah, it's negative.
Oh, you're the best. For 3, it's -8? eyes are going, and when I apologize, thanks for telling me that. And when you saw me read my calculator, and what I said it was?
Where did you get those,
What's that?
those points, 2 and negative 1? I forgot.
Oh, right there.
Oh,
And what are they called? There's a name for these. They're called the critical points.
oh, okay.
And
So
how do you find critical
points
points?
and then
It's points are what? First derivative of x equals 0. They're x values, but first derivative of x equals 0, or we're at what?
Those are the-
D and E. But we didn't have to worry about that. We didn't have any fraction or anything, true?
Will we ever have to like get one where you're not gonna give us an interval? So
That's
we can
next
ju-
class.
So we can just find
He
it.
knows what's coming up. This, what we're talking about right now, everyone, will last, not only from 4.1. This will go all the way up to 4.3. We will be doing this all the time, but you just hit on it. You go, what if you don't have endpoints? Then we're looking at the locals or relatives, and we'll go find all the relative extrema. Find the relative or local extrema. Cool? Hey, now, the language. This is what we gotta end on today, Owen. The language, the communication. Students mess this up. We're gonna make sure on day 1 we never mess this up. Like, how do I speak? And students do this. Listen to this. Oh, okay. So the absolute max is -1. And what do you mean? That's the highest number, right? So the answer to this question, the absolute max is -1. And the language is wrong. I'm not speaking correctly. What should I say? What is the absolute max?
8 at
It's
x
the
equals.
y value.
Yep.
So this is how you communicate. So this is what I would say. Ready? Ready? On the interval. What was the interval again?
-2 and 3.
On the interval -2 to 3. Right? At x equal to, I'm gonna fill in a blank, the absolute max is, and I'll fill in a blank. You know what I might do? I may already write that for you. And then you fill in the what? Blanks. But if you ever wanted to write this on your own, you could speak like this. Okay, so on the interval -2, 3, the absolute max
At x
of
equals.
f, I should say, a function f of x is, what goes here? The y value, which is the what?
8,
What's this value?
-1.
Cool. Now let's do another one for the min. That one on the interval, same interval, -2 to 3. See, I like to write that again on my test, just to remind a student, in case they forgot, there's endpoints. You're only on that interval, right,
Yeah.
Belraj? It's gonna be things tight off here, all right? At x equal to, you gotta fill this in, the absolute min for minimum, of f is, let me put a blank. What's this? Which one was the
2,
lowest?
2 and -19.
-19, this was a. So I'll tell you where this gets forgotten though. So I'll present that like that, right? The final exam. You heard me saying I like to do a lot of multiple choice problems, right? But I also like to do some pre-response questions. And I'll have a problem, I give you a function, and I'll say, find the absolute extrema, okay? And you'll go through this problems. You'll go through this process. But it's there, I think. Maybe they're in the final exam mode, right? They're in the final exam mode, and guess how they write the answer? They go, the absolute max is -1. Right? Or they just circle -1. And they forgot the language. What's the language? We gotta say the max is what? The y value, it occurs at. Do you follow me? So it occurs at x equal to -1, but it is what? 8. Do you know why it's so important we speak like that? Why it's the y value?
Because there could be like.
It could be like temperature. So watch this. This is, I promise we'll go right for this. We got a temperature function going. Look at this. And here's June, right? Day 1, 0 to what? 30? June have 30 days? All right. And the temperature went like this, right? Let's just say, and it went like this. Went up here, went like this. On June 16th, it got to like 98 or something, all right? And it came down like this. All right, so you're saying this. Listen to this language. So the absolute max, this is F. You know it's temperature, true? I go, oh yeah, the absolute max is at 28. Or the absolute max is 28. 28 degrees Fahrenheit? What am I messing up? It occurred on the 28th day. It occurred on the 28th day. What was that absolute maximum temperature? It was what? 98 degrees Fahrenheit. Do you see how they messed The language is you're reporting the y value as the absolute what? Maximum. This can model something in real life, like temperature. We don't, oh, the absolute max is that, no. The absolute max is 28. No, the absolute max is 98 degrees. When did it occur? On which day? The 28th day. Cool? All right. Hey, we didn't finish off 4-1, but we got into it. Have a great day. Valorant, we didn't finish 4-1.
No.
Some other little things in there. They got some graphs. They got some graphs. So, all right, I want to point out we didn't do all 4-1.
Okay.
Because remember we did, remember when we drew derivative graphs? They do something where they draw a derivative graph and they want you to draw out. They want you to get an idea, and we'll do that. Yes! What class? Oh, I don't know.